topic is
hybridization is the mixing of two atomic orbitals to give rise to a new type of hybridized orbital. We know the sp3 is spherical pxyz axis. Let's look at the hybridization of carbon. So in the sp3 hybridization, one s orbital of that energy level combines with the p orbital of that energy level to form 4 degenerate orbitals. Even though they are from the same energy level, according to Hofbau's principle, the p is still on a higher energy level than the s. Now let's look at the sp2 orbital. Here, s combines with the p orbitals on the same energy level to form the sp2 hybridized orbital, leaving one p orbital unhybridized. Bonding, the sp2 hybridized orbital can form another bond with an sp2, forming a sigma bond, and the unhybridized will form a pi bond. Finally, for the sp hybridization, s will form with 3 p orbitals in the same energy level to form the sp hybridized orbital and 2 unhybridized orbital. So guys, here is just a chart to show you other types of hybridization with their electric domain geometry and their molecular geometry. For an sp orbital, it's going to be linear, having a bond angle of 180 degrees. For an sp2, it's going to be trigonal planar, bent, having 120 degrees. An example is BF3. We know linear can be carbon dioxide. sp3 is going to be tetrahedral, methane, ammonia. Then sp3d, trigonal pyramidal. This is going to have 120 and 90 degrees. For sp3d2 is going to be octahedral, 90 degrees only. An example of sp3d is PCl5. sp3d2 is SiFe6. That's our hexafluorosilicic acid. So now, how do we determine all this hybridization? Here is an easy trick. We can see around the s atom we have 2 sigma bonds and 1 lone pair. So the summation of both of them is going to give us 3, which is leading to the hybridization of sp2. Around the oxygen atom, the number of sigma bonds here is 1 plus 2 lone pair electrons, that's sp2 in total. Remember, it's going to be the same sigma bond on the left and right hand side. And that's all for today.